Okay, so last time we talked about, oh my gosh, what did we talk about last time? Oh yeah, we talked about integration by parts. Okay, so we're moving forward talking about different integration techniques. So basically these are the integration techniques when you need to find like a fundamental, you need to find an antiderivative so that you can use the fundamental theorem of calculus. So like integration by parts is very useful for that. So like there's certain functions where integrals, when you look at them, you're like, oh no, I have no idea what the antiderivative of that is, right? Integration by parts helps you find the antiderivative. Today we're going to talk about another example of that sort of that happening, and it's called trigonometric integrals. So let's go to writing mode. Okay, that's not it. There we go. Okay, so we're going to talk about trigonometric integrals. So obviously, or not obviously, I don't know what the proper term I should use is, but you know how to find things like, well, what's the antiderivative of cosine? So we know that the antiderivative of cosine is sine. And why is that? Well, because we know that the derivative of cosine is equal to sine. Or sorry. Let's rewrite this. You know this because the derivative of sine, there we go, is equal to cosine. I was like, wait, I'm not doing this right. Okay, so this is just a simple case of rewriting the derivative rule into an antiderivative rule. So rewrite derivative rule as an antiderivative rule. Okay, these are like the easiest, this is like the simplest case to figure out what your antiderivative is. And you can just take a derivative rule and rewrite it. Okay, so we know like the antiderivative of cosine is sine. We also know that the antiderivative of sine is equal to minus cosine. And why is that? Well, because if we take the derivative of minus cosine, you get sine. Okay, now it gets more difficult when you start like adding extra stuff to this. So like as an example, as an example, there we go. Let's say, let's write example. Let's say that you're looking for, I don't know, the antiderivative of cosine cubed times sine. Okay, so you look at this and you're like, I don't know off the top of my head a derivative rule that can rewrite to give you this. So in some cases, like, you already have like a bag of tricks that you can use. Like sometimes you might want to use u substitution. So if you look at this, like you're like, okay, let's set u equal to be cosine, which means that the derivative of u with respect to x will be sine. And you look at this, you're like, oh, this is good. Like, I have like a cosine right here, and you're like, oh, I have like a sine right here. So if you multiply both sides by dx, you get the differential du equals sine x dx. And that's even better because this now matches, right? So you could do like a u substitution in this case. You're like, okay, I can rewrite this. My cosine cubed x, that's just u cubed. And sine x dx, that quite simply is my du. Right? Because those two things are equal. And then you look at this and you're like, oh, okay, this is not that bad. I know how to integrate u cubed. That's going to be 1/4 u to the 4th plus c. And then I can substitute back in what my u is equal to. My antiderivative is 1/4. My u is cosine, so I'm going to get cosine to the 4th x plus c. So yeah, I have my antiderivative. Boom. Not bad. And actually what you notice is that there's like a general pattern that you can notice here. This will work as long as you have cosine to some power n times sine. Because no matter what, you can set your u equal to cosine. Which means my du dx will be equal to sine. Which means my differential du will be equal to sine x dx. And then you look at this, you're like, oh, okay, my sine x dx right here, I'll be able to replace with du. So that will become du. And then my cosine to some power, well, that's just u to some power. And I know how to integrate u to some power. That is going to be 1 over n plus 1 u to the n plus 1 plus c. Meaning I'm just going to get 1 over n plus 1. My u is cosine, so I'll get cosine to the n plus 1x plus c. So like this will work as long as you have cosine to a power multiplied by sine to a power. Okay. I'm going to pause for a moment. So I'm going to leave this here so you can write. You can also think of questions that you might want to ask me. So this is like just a straightforward application of u substitution. We're just going to go over like a lot of the different cases that you encounter with trig functions like this when you're integrating them, because we're going to sort of build up our like tool house of like things that we're going to do and like approaches we're going to use. Okay. So is there anything I can answer about this? Any questions so far? Okay. Let's look at a more complex example then. Okay, so with the previous example we had cosine to some power times sine. So what about if we have cosine to some power, like cosine squared x, times sine is also going to be to a power, like sine cubed. Okay, so notice that I can't just set u equal to cosine, because my du dx would be sine, which means my differential du would be sine x dx. Because I can't just replace this with du, right? Because it's not just sine x dx, it's sine to some power dx. So that's not going to work. Sad face. So what can we do? So actually, you can be sort of tricky about it. It's sort of cool. So if you look at this term right here, it's right over here, we're looking at sine cubed x dx. Well, you could rewrite this as sine squared x times sine x dx. Okay. So we're like, okay, let's take that, let's break it up. Now, what's the purpose of breaking this up? Well, you can use some trigonometric substitutions. Okay, what do we know that sine squared is equal to? Well, there's a lot of different things, but one of the things in particular that we can set it equal to is 1 minus cosine squared. Okay. So this integral, let's rewrite it now. You get the integral of cosine squared x times 1 minus cosine squared x sine x dx. Okay. Now we can make some substitutions here. And actually, I made a mistake earlier with this. I'm going to move it down. Let's move it to right here. What mistake did I make here in blue? I messed up. So if you look at this stuff, yeah, I forgot to put the minus. So let's update that. When you take the derivative of cosine, you should get minus sine, which means my du would be equal to minus sine x dx. Yeah, it's so easy just to forget that damn minus. Okay, so I have a sine x dx right here. Sine x dx is equal to minus du, right? Does it make sense? I just move my minus from the right hand side to the left hand side. So this is going to be minus du. Now I can make some other substitutions. My cosine squared is u squared. And my 1 minus cosine squared is 1 minus u squared. So actually we can do u substitution, but it required doing some clever rewriting first, right? Like remember at the beginning I was like, oh no, we can't just set u equal to cosine and then go from there. Well, it did work after we rewrote that sine cubed, right? And notice, why did it work? Because I was able to rewrite my sine cubed as a sine squared times a sine, right? So this will actually work as long as you have sine to an odd power. Because if you have sine to an odd power, what you're going to get is sine to some even power times sine, right? Because if you have an odd number and if you subtract 1, you'll get an even power. And then any even power of sine, you'll be able to rewrite it as like 1 minus cosine squared to some power. So this will actually work as long as this number here is odd. But back to solving my integral. You can multiply that through and you're going to get u squared minus u to the 4th. We can factor out the minus and then you get du. Which will give us minus the antiderivative of u squared is 1/3 u cubed minus 1/5 u to the 5th. And then I can substitute back in what they're equal to. If you distribute the minus, you'll get 1/5. My u is cosine to the 5th x minus 1/3 u is cosine to the 3rd x. And that is your antiderivative. So I'm going to pause for a moment. So let's generalize this. Let's say that you have the antiderivative of cosine to some power n times the sine of some power m. And we know that m is odd. So if m is odd, then what I can rewrite this as is sine to the m minus 1x times sine x dx. And if m is odd, what can you say about m minus 1? So if m is odd, what can you say about that number minus 1? It will be what? Even, right? Which means that now this m minus 1 right here is even, right? Which means that really what this is sine 2 times some number j. Right? So 2j equals m minus 1. Right? Because we said m minus 1 is an even number. If m minus 1 is an even number, it's divisible by 2, right? So it's equal to 2 times something. Now, if it's equal to 2 times j, that means that I can rewrite this as sine squared x raised to what power? What is that whole sine squared going to be raised to? Yes, to the power j, right? Because how do exponents work? If you have x to the a to the b, that's equal to x a times b, right? So 2 to the j means that originally it's equal to sine to the power of 2 times j. And this is multiplied by sine x dx. Which means our original integral can be rewritten as cosine to the n x times sine squared x to the j times sine x dx. And we can rewrite this as cosine to the n x times, now what can you rewrite sine squared as? 1 minus cosine squared all to the j sine x dx. And now you're ripe to do your u substitution. I'll set my u equal to cosine x, which means my du is going to be equal to minus sine x dx. Should put that in blue. So my du will be equal to minus, actually, yeah, my du will be equal to minus sine x dx, which means that minus du equals sine x dx. So looking at this, you're like, oh, okay, well, I have a sine x dx right here. I can replace that with my minus du. I can distribute the cosine to the n and the into here, and I'll get cosine to the nx minus cosine to the n plus 2x, all raised to the j. And then you, after multiplying that out, you'll be able to integrate it and you'll get your answer. Okay, so this will always work, basically. My point is that if you have some power of cosine times some power of sine, and the power of sine is odd, then you're going to be able to do this, is the whole point. So I'm going to pause. Let's see if there are any questions. And also just allow people to write. Okay. Okay. I'm going to go forward. Let's do another example. This will be a different type. So let's say, so we've been using this like setting u equal to cosine, because then you get that du equals like minus sine x dx, right? So this is really useful if you have a cosine and a sine in the integral. But what if you only have like a power of sine in the integral? So let's say I have sine squared x dx. Can I just set u equal to sine x to solve this? Yeah, you're like, man, I can't just do this because then my du would be equal to cosine x dx, and then it's like, well, there's no cosine, right? So you're like, this is not going to work out. So you're like, shit, u substitution doesn't look like it's going to work for this example. Does that sort of make sense to everyone? Like, our go-to has been like, let's just use u substitution. And you look at this, you're like, not going to work. So other than u substitution, what do we have available to us? Yeah, integration by parts. Interestingly enough, integration by parts is not going to work here because what you would get is repeated integration by parts forever. Let's just put integration by parts, IBP. Because to use integration by parts, you need to figure out what your u and your dv are. And sine, if you keep on, so you need something that, you would need your u to be something like x squared, so that eventually if you took the derivative of that, like it would go down by a power, but the cosine or sine would not do that. So integration by parts would not work. Just to tell you that. So integration, you should actually make a note to yourself about that. if you want to be able to do integration by parts, your u needs to be equal to something so that when you take its derivative, like, it will eventually go away. So like this one, you'd have to do repeated integration by parts. Your u would be equal to 2x. And then what do you get when you take the derivative of that? 2, right? Remember we did an example where you had to do integration by parts twice? Okay, that's not going to work here because if you set like your u equal to a sine, you're just going to get cosine. And then you have to do integration by parts on that. And if you set u equal to cosine, you'll just get minus sine back and we'll keep like cycling. Okay, so if you look at this one, actually what you'd want to do is more trig identities. That's why you learn all of them in pre-calc. So do you remember the power reduction identities? Sine squared is equal to 1 minus cosine 2x over 2. Do you remember that? It's called the power reduction identity. So using this, you can rewrite the integral as 1 minus cosine 2x over 2, which then we can break up into two fractions. You'll get the integral of 1/2 minus the integral of 1/2 cosine 2x. And then let's break that up into two separate integrals. You'll get the integral of, you'll get 1/2 integral dx minus 1/2 integral cosine 2x dx. Now, the first one's easiest to solve. If you integrate dx, you just get x, right? So we get 1/2 x. Hooray! Now the second one's a little more complicated. So you look at this, and you could do a u substitution. I'm going to set u equal to 2x. Because then my du will be equal to 2dx. And you realize that this integral can be rewritten as the integral of the cosine of u du. And actually, this du is 2dx, right? So actually, we need to change that ever so slightly. Because otherwise they're not going to match up. I only have a dx right here. So I need to solve this for dx. Right, what is dx equal to? Yeah, half du. So actually what you get, let's move that over. Actually what you get is the integral of the cosine of u. I replace the dx with 1/2 du. So I can move that 1/2 out in front. Now what is the antiderivative of cosine u? You'll get 1/2 sine of u plus c. And then you can plug the u back in. You get 1/2 of the sine of 2x plus c. So that goes right here. And then you can just put the plus c out here. Because if you distribute the half to the c, it just ends up being c. So you get 1/2 x minus 1/4 sine of 2x plus c. There's your antiderivative. So I'm going to pause, just in case there are questions, which there might be, and you might need to take a moment to look at it. Should draw a little box here. I'm calculating this integral over here. I boxed the dx because you needed to isolate the dx and the du equals 2dx. Right, because notice you get the 1/2 times 1/2 sine of 2x. Oof. I'm a little sleepy. It's like the middle of the day. It's like nap time. I'll be honest, it is sort of nice being at home because I can just take a nap. Like, I literally just walk over to my bed and take a nap in the middle of the day. Like, if I was on campus, I couldn't do that. Although, if you've ever been to my office, what do I have in my office? For people who have been to my office. Oh yeah, this is a whole lot of notes. Are we talking about like what I wrote on the screen right here? I have something better than a cot. Okay, maybe not as cool as a hammock, but like I can use it for a similar purpose. It's more multifunctional. I have a nice couch in my office. I used to just lay it down on the ground. I'd have like a little pillow and a yoga mat, and I would just like roll it out and lay down. Oh man, the lazy boy. Oh no, I have not gotten one of those. Let me explain the dx part though. Okay, so if you look at this integral here, cosine 2x dx, our u is equal to 2x, so the cosine 2x becomes cosine of u. Now here's the problem. If u equals 2x, then du equals 2dx, which means I can only replace 2dx with du, but I don't have 2dx, I only have dx. So what I did is I took this equation right here, and I solved it for dx to figure out what I could replace it with. So you solve that, you multiply both sides by 1/2, which means what can I replace dx with? 1/2 du. So that's why I get the 1/2 du right here. The dx, it was replaced with 1/2 du. No problem. For people who haven't been in my course before, I had this dream that like I'd have like a lazy boy, like sort of like what they have like in that one movie WALL-E, you know, where they have like those little like things they like roll around on. It'd be like a lazy boy with like a joystick, and I could just like wheel it around. Does that make sense? Does everyone know what like a lazy boy is? Like a recliner chair? And like what I imagine, I'm just gonna draw this. So like, this would like be me on it. Right, and there'd be like a joystick right here. And then what I'd have is like wheels. So I could like wheel it around. Yeah, I'd be like Dr. Xavier. But like more importantly, what I imagine is that like, so like if this is like the board that I'm writing on, like let's say I couldn't reach to write there. Like, you know, my hand is right here and I'm drawing. Like, the whole thing would just, like, raise itself up like a cherry picker. Yeah, it's like a 22-inch rims. So, like, what I imagine is, like, it would, like, be able to, like, you know, like, raise me up. So, like, I don't know, like, I'll just, like, quickly draw, like, what I imagine. Like, here would be, like, the wheels and, like, the axle. And then, like, the whole system would just sort of, like, raise me up. And then, like, now my lazy boy would be, like, elevated in the air. And there I would be like sitting on it. So if I needed to reach anything, does that make sense? It'd be like the ultimate mobility device. Does everyone get what I mean? Like it would just like be raised up, like you've ever seen those things where it's like they're like this, and then they can sort of like go like that, so that like it lifts the platform up. It'd be something like that. Oh my god, I wish. Okay, but have I answered your questions about integrating here? Yeah. Shall we move on to a different example? Yeah. Okay. Let's do another one. This used to be really important back in the day. It's not so important to know how to do this nowadays because you have like Wolfram to do things for you numerically, but it's still useful for a lot of physics stuff. So let's do an example that might involve more tricks. We're going to have cosine to the 8th times sine to the 5th dx. Okay, so the first thing we're going to concentrate on is this part. Now, why are we looking at that part? Exactly, right? And it's like we had that whole thing where you can factor out, we can look at this and we're like, oh, well, my sine to the 5th x dx, I can rewrite that as sine to the 4th times sine dx. And then that sine to the 4th is sine squared, right? And then what am I gonna, now I can replace that sine squared inside there. So you're like, oh, okay, well this is 1 minus cosine squared x. One minus cosine squared x, all squared sine x dx. Okay, so let's rewrite this. We've got antiderivative of cosine to the 8th x multiplied by 1 minus cosine squared x squared sine x dx. And now I can finally make my u substitution. I'm like, oh yeah, let's just let u equal to be cosine. And then you're like, okay, cool, let's do those replacements now. I get antiderivative u to the 8th times 1 minus u squared, all squared. Now if your du is cosine x, then your du dx is minus sine x dx. So I have a sine x dx right here, but I have this minus that I need to get rid of. Oops, and then also, I already moved the dx over, so that's not supposed to be there. Which means that minus du is equal to sine x dx. You're like, oh yeah, okay, this is just minus du now. Okay, now you look at this and you're like, okay, I can work with this. I've got my u to the 8th times 1 minus u squared, quantity squared. We're going to have to multiply that out. So you get what? U to the 8th. So if you multiply that out, you're going to get 1 minus 2 u squared plus u to the 4th. I feel like I screwed that up. I think that's right though. Because if you have a minus b quantity squared, you're going to get a squared minus 2ab plus b squared. Yeah. Okay, cool. Okay, which means we can multiply this through and we're going to get u to the 8th minus 2u to the 10th plus u to the 12th. Yeah. Okay. I can like sort of feel my brain just slowing down. I feel like they're gears and someone threw sand in the gears all of a sudden. Does that make sense? Like all of a sudden it's like something happened to my processing and I'm like, no! Why? Why, brain? Why you failed me now? Okay, so now you have to be careful. Don't forget about this minus right here. Yeah, no, it's a thing. So do you see this minus from the du? Yeah, the sand in the gears is a real thing. I'm going to multiply all that through. So when I put it back inside, I'm going to get minus u to the 8th plus 2u to the 10th minus u to the 12th du. Does it make sense to everyone? I had to change the order because of the minus in front of the du. If you forget that, it's all screwed up. And then you're like, oh shit, I can actually integrate this. That's good. So what am I going to get? I'm going to get a minus 1/9 u to the 9th plus 2/11 u to the 11th minus 1/12, actually minus 1/13 u to the 13th plus some c. And then now you just plug your u back in and you're like, oh shit, my antiderivative is minus 1/9 cosine to the 9th x plus 2/11 cosine to the 11th x minus 1/13 cosine to the 13th plus c. Victory. I claim victory. That is my antiderivative. It's like really what you need to remember is like all you're doing is basically breaking stuff up. The real key here is that you're looking for those odd powers of sine so that you can... So notice what you were doing before is you started off with a problem that had cosines and sines. Notice now at the end of it I only have cosines. Right? So like the whole point of finding that odd power of sine is that you can rewrite everything as just cosines with that one leftover sine so you can do the u substitution. Bam. This is a lot, huh? I mean, actually, it is and it isn't. It's like the same thing, just more complicated. There's just a lot of writing. I'm so happy, though. Oh, thank you. Thank you for saying that I explained it well. I, like, really tried to, like, break it down to, like, the key aspects. Like, what are you really looking for? Like, what you're doing is you're starting off, like I said, with a mixture of sines and cosines. And you want to end up with something that's all cosines except for a single sine. Okay, people are asking me about the midterm. It's take home. You can work on it. I'm not going to give you the answers. Go back and watch the pumping questions. Remember, you're just dealing with a curve. Also, more importantly, for a bunch of them, you're going to, what's it called? use Wolfram to numerically calculate it for you. So what you need to do is set up your integrals. I'm just gonna say that. How much time do we have left too? What time are we supposed to end? Oh, yeah, there's not enough time to do another example. What do we do when there's not enough time for another example? The professor from the people.